As I told you, the Big Bang Theory had been studied for a very, very long time, decades. And any good idea in science, whether it is a hypothesis, an idea, or a theory, is going to be backed up by evidence. And so the first piece of evidence you would look for trying to explain that there was a big expansion is that if everything was condensed together at one point in time and as it expanded apart, then it should still be expanding. And so this is what scientists first came across. And the gentleman who found out about this, his name was Edwin Hubble, the same Hubble that they named the Hubble Space Telescope after. And what he was able to determine was he was using a telescope, and at that time, in the early 20s, astronomers thought the only galaxy there was the Milky Way galaxy. Even though they saw some other fuzzy patches in the sky, they called them nebulae. But what he did was he was looking through a telescope at them, and he not only looked at them with a telescope, but he attached a spectroscope to it so he could look at the spectra of those galaxies, those fuzzy patches. And what he found was that there was a certain amount of redshift to them, meaning that if you have a spectra of a galaxy or an object at rest, it's going to have lines located in these areas like you see on this particular one. And if it's moving towards you, you're going to see a shift in where those lines are located to the blue side of the spectrum. And you can see that in this one, how they do not line up. And then if it's moving away from you, you will see a shift in the other direction, which you see here. Now, Hubble observed this in every single one of those fuzzy patches that he looked at, and he realized that what they were galaxies, and every single one he looked at was moving away. And this is what's called cosmic redshift. And cosmic redshift shows us that the universe is still expanding. And if it's still expanding, it had to be closer together at one point in time. And so this was the first piece of evidence that was supported by that. Now, the second one is obvious also, because if somewhere they detonated a nuclear bomb and I said, hey, we're going to take a field trip and we're going to go look at that area and walk around and check it out, most of you wouldn't want to go. And the reason being is because there would be leftover radiation, which would be bad for you. And so what you're saying from this is that if there's a large energetic event, there should be leftover radiation from that event. And the Big Bang was the largest event, most energetic event that had ever happened ever. And so there should be leftover radiation. And so scientists knew they should look for it. And they looked for it, and they looked for it, and they looked for it for 40 years, and they couldn't find it. And then two guys were working for Bell Laboratories using a big radio receiver communicating with a telecommunications satellite in orbit around the planet. And they were having trouble. They were getting fuzzy static every time they tried to communicate with this. And they cleaned the device. They checked everything out. They did everything they could think of. Meanwhile, down the road at Princeton University were some scientists who were trying to locate this leftover radiation. And these two gentlemen working for Bell Laboratories, Penzias and Wilson were their last names, they had discovered the leftover radiation from the Big Bang. It's called cosmic background radiation. And it's everywhere. It doesn't matter where it's at. And it's calculated at exactly the temperature that they would expect it to have cooled off to over these billions of years since this big expansion. So in 1989, NASA launched a spacecraft called the COBE, which basically mapped the universe and the distribution of that temperature throughout the entire universe. And what we see then is these different areas, darker areas and greener and yellow areas showing different concentrations of matter shortly after that Big Bang event. Now, about 12 years later, they launched the WMAP. This one was like, the COBE was like the very, very simple version, gave us some idea. And then the W map was like the digital version, which was much more precise. You can see a lot more detail in this about the distribution of where this material was, how specific it is, and it gives us a great understanding of what's happening right after that Big Bang event. So we have these two powerful pieces of evidence showing that the universe is still expanding and that there's leftover radiation from that event. There's a third one which talks about the distribution of elements and how much of the universe should be made of hydrogen and helium, and those predicted amounts are exactly what we measure. So all of these things show that this event did occur.